Okay, the first part of understanding the history of computing is actually nothing to do with computers at all. It's about understanding a particular kind of counting. It's about understanding binary. So the objectives of this part of the module are just to explain to you why this is so, and to explain to you that all computing really is processing ones and noughts. So let's illustrate that straight away. You're watching a video, it's stored on a computer a long way away from you. That video is stored in that computer just as a collection of ones and noughts. It's a very sophisticated collection of ones and noughts, and you're using some clever software that's capable of translating those ones and noughts into the video you're looking at, the picture you're looking at, and the voice you're listening to. But basically all you're doing is you're getting a sequence of ones and noughts, and your software is doing clever things to display a video and display you sound. Let's have a look at a joke. It's not a very good joke, but if you immediately read that joke, you might read it as there are 10 kinds of people in the world, those who understand binary and those who don't. Obviously, that doesn't make any sort of sense. If you understand binary, you know what the joke is. The joke is that in binary, 1 0 is equivalent to the decimal number 2. So if you understand binary and you interpret 1 0 as being a binary number, not a decimal number, then it actually reads as there are 2 kinds of people in the world, those who understand binary and those who don't. So what binary is just base 2 mathematics. It's a kind of maths where there are 2 symbols, 1 and 0, and you basically work like that. Humans obviously find it easier to think in base 10 decimal, or what's sometimes called denary, and that's probably because we tend to have 10 digits, and it's just a more natural way of thinking because that's the way we've always done it. Computers, on the other hand, don't have digits or hands or whatever, and it's easier for them to be developed to process things using just 2 symbols, 1 and 0. Let's have a look at why that might be. Let's start by thinking about what a bit is. Now, a bit is the smallest piece of data you can actually imagine that can be stored on a computer. The single tiniest fact that a computer can actually store. And if you think this through, what this actually is 1 or 0. A simple value stored on a disk or in memory or something like that. It's either 1 or it's 0. If we change the terminology slightly, we can think of it as either on or off. So a piece of disk could be magnetized positively, that's on, not magnetized negatively, that's off. Or a particular part of a circuit could have a current flowing down it, that's on, or no current going down it, that's off. So it's the same idea, just in a slightly different way. Another way we'll meet later on is thinking of this in terms as true and false. So true is on, is 1, false is off, is 0. So a computer might be programmed to believe that if a current is flowing down a particular circuit, a certain proposition is true, or a certain statement is true, or a certain operation must happen. Let's make this discussion of storage a little bit more useful. A bit, after all, isn't actually going to be any use, and if all a computer can do is process a single bit, then we're not going to get very far. So the next bit unit up of any use is a byte. A byte is usually 8 bits. It can be different in different computer architectures, but these days it's almost always 8. So that's a little bit more useful. It's useful to people that are concerned with precisely how quickly computers are working and who work at a very low level, but you wouldn't get much MP3 file in a byte, so let's pass on to something more useful. A kilobyte is 1,000 bytes. Some might argue it's actually 1,024, but we'll keep the mathematics simple and think of it as 1,000. Now, not so long ago, a kilobyte was an incredible amount of memory. Early home micros came out with only a single kilobyte of memory, and that was enough to run some quite reasonable applications. But these days, again, you're not going to get much MP3 for your money out of a kilobyte. So the smallest useful measure of memory or storage these days tends to be a megabyte, which is 1,000, or if you want, 1,024 kilobytes, which you might get a good few seconds of your MP3 file out of. But remember that all a megabyte is a collection of ones and noughts. If you've got a calculator handy, you might now want to have a look. So a megabyte is 1,000 kilobytes, a kilobyte is 1,000 bytes, a byte is 8 bits. So how many bits are there in a megabyte? It's a very big number, but remember, all it is a collection of ones and noughts. All a megabyte is a collection of ones and noughts. that 5 megabyte MP3 file you've got is just a big long collection of ones and noughts that certain software can interpret in a particular way to play a nice music track to you. That's binary. That's binary counting. We would read it as 0, 1, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, 1, 0, 0, 0. We'd never say 1,000 or 100 because obviously that's a bit confusing and doesn't really make sense in binary. But just have a look at that and understand how a computer would count just by flicking switches or setting currents to flow down different cables or whatever. And to finish with, have a look at these numbers here. They're just powers of 2. And jot those down, and jot down some counting in binary, and see if you can spot the relationship between those numbers there and binary, and see if you can understand why those numbers are so particularly important to computer scientists. Right, we've nailed down what binary is. What we can actually do now is carry on to look at why this is important and why this is fundamental to the development of the history of computing. And surprisingly, the story we're going to look at starts a very long time ago, in fact, the early 18th century.